This video lecture is going to look at 4 sample programs that illustrate some basic features of the PIC24. 2 of the subsystems that will be discussed are going to be the parallel port subsystem and the serial port subsystem. We will discuss those in much more detail in later lectures. This is simply going to give you your first introduction to how those subsystems work. The first sample program we look at is called LED Flash No Macros.c, and this can be found in the code archive under Chapter 8. All of our programs have an associated .mcp MPLAB project file associated with them. You can open an MPLAB and compile. This program does a simple task of blinking the LED that's connected to port RB15 on the PIC24 as discussed on the PIC24 startup schematic. All of our programs are going to have at the top a #include PIC24 all.h. This header file includes all the header files that are included with our libraries, as well as microchip specific header files needed for proper compilation of PIC24 programs. The entry point for all C programs is called main. Recall that main is called by the C runtime code after global variables have been initialized. The first line following main is a call to a C function called config clock. This is a function that's provided in our custom libraries. This is going to configure the clocking subsystem to the PIC24, and we have it set up in our lab exercises to choose the fast RC oscillator along with the PLL to produce a clock frequency of 80 megahertz. Following the config clock statement, there's a assignment to a special function register bit that's called ODC B15 that's going to configure this pin for a special configuration called open drain. Recall that in our coverage of the PIC24 startup schematic that we said that this particular connection for a parallel port to an LED is not a typical connection to drive an LED. We're doing it in this way in order to actually for this LED to serve 2 purposes. One, we'll be able to blink it via this connection, or it will simply be on once power is supplied. We're going to talk more about what an open drain configuration is in a later lecture. Let's just take it for now that assigning this special function bit to a 1 will configure this output pin to be open drain. This next assignment statement here is going to assign this special function register bit TRISB TRISB15 to a 0. It turns out that port pins on the PIC24 can be configured as either inputs or outputs. In this case, we want this to be an output, which means that it's going to be able to either drive this pin low or drive this pin high. And in that case, in order to configure as an output, we need to set the special function register bit to a 0. Later on, we'll discover that if this bit is set to a 1, it'll configure that particular pin as an input. But in this case, we need to configure as an output, so we'll set this special function bit TRISB15 to a 0. This next assignment here, _lat B15, is the way that we're going to set an output pin either high or low. In this case, we're assigning it to a 0, so that means that we're going to be driving this pin to a low voltage, the same as tying it to ground, and a 0 voltage here, and ground is a 0 voltage here, means that there's no current flowing in this LED, which means that this LED would be off. So this is essentially saying we want this LED turned off before we enter this loop here. So we saw that these 2 statements here configured this port, while this statement here assigned an initial value of 0 volts. At that point, we're going to enter an infinite while loop. This while loop is an infinite while loop because there's a 1 for the exit condition. That means the exit condition will never be true, which means we will never exit this loop. Why do we have an infinite while loop? It's because if we exit this loop, we have nowhere to go. We always want to be executing this code while power is applied to the processor, so we'll do that by having this infinite while loop. All of our mains will have an infinite while loop at the end of them. These 2 statements form the body of the infinite while loop. This first statement here is simply a delay for a period of time. Once we delayed for a period of time, what we want to do is we want to turn this LED from an off condition to an on condition, or vice versa. So to do that, we're going to take the value that is currently driving this port, in this case it'll be a 0, we'll do a logical negation of that, which means that this would become a 1, which means we would then assign this output pin a value of 1, turning the LED on. We'll then hit the end of the loop, come back up here, delay again. At this point, the LED would be on, and so this value here would be a 1. So a logical negation of 1 is going to be a 0. So now we're going to turn the LED back off, and so forth. So we'll simply always be executing the code in this loop, which is going to delay and then flip the status of this output pin here, either turning the LED on or turning it off. This delay function is implemented by this code up here, which simply has a couple of loops that loop for some fixed amount of time, simply executing code and essentially wasting processor time. The amount of time that this is actually a delay for is going to be dependent upon the clock speed of the processor. But in this particular case, it turns out the delay is long enough so we can actually see this LED blink. If this delay is not long enough, then we would see this LED sort of dimly on instead of it actually physically blinking. What is long enough? Long enough means that it has to be on for, a 50 to 100 milliseconds or so minimum in order to actually, see that thing blinking. This example, ledflash.c, does exactly the same thing as the previous code does, except it's written in a style that's going to be used for the remaining examples in this book. First of all, it makes use of macros for configuring ports. This macro right here says config LED1. If we go and take a look at how that's defined, it's actually defined to use yet another macro called config RB15 as dig OD output. This is a macro that we provide in our library, and what it does is it will configure port RB14 as a digital open drain output. Inside this macro here are going to be the same bit settings that was in the previous code, except that now you don't have to remember these bit settings. Instead, you just simply have to remember this macro name, which is more readable than just writing this code here. Here we're renaming this macro as config LED1 to even make it even more readable, so when somebody looks at this code, they can see, oh, this is configuring an output port for an LED. It doesn't actually tell them what port is being configured. That's actually hidden inside this macro. It turns out that we're configuring port RB15. But what if we wanted to configure port RB14 or RB13? We'd have to just change the code here and not change anything down in our main code down here. We're also going to use a macro when assigning a port a value. In this case, we have the macro LED1 is being assigned a value of 0. We do this for two reasons, both readability and maintainability. Readability means that we're using a meaningful name, in this case LED1, to indicate that there's an LED on this port. Maintainability is that we're hiding the fact that this particular LED is on port 15. That way, if we wanted to change this in the future, perhaps we wanted to change this to port 13, then we only got to change this on these two places here and don't have to change it anywhere down here in our code. Recall that before blinking the LED, we need a delay so that the blinking of the LED is actually visible. The previous code had this function called a delay, which used two nested loops to implement a software delay. The problem with this approach is that the delay is unclear as to how long it will actually be, and it's also going to be dependent upon the clock speed of the processor. If we change the clock speed of the processor, the delay of this function is going to change. What we really want is a function that where we can specify the amount of delay that we need. We provide a delay function in this file here. It's a delay macro where it's called delay_ms, and this parameter here is going to be the number of milliseconds that this function is going to delay before the next function is executed. This is still a software delay, but it knows about the clock period. So if you change the clock period of the processor, it will still delay this amount of time. The other thing that this delay function does is that it will blink the heartbeat LED while it's waiting. In the discussion of the PIC24 startup schematic, we talked about this serial port connection that is going to be used to connect your PIC24 to your portable PC. We're going to use this for two purposes. One, it's going to be used for ASCII input and output to your program. That means you'll be able to enter characters to your program, and your program will be able to print out messages via special library functions that we'll give you. We're also going to use this link for downloading new programs via a special program called a bootloader that you'll discuss in lab. This program, echo.c, demonstrates some basic ASCII input and output using the serial interface that was mentioned on the previous slide. Starting in main, we still have the config clock function here, but we've added some more configuration functions as well. This config heartbeat function configures RB15 to blink the LED, as we've mentioned previously. We're going to use this as a heartbeat LED, and what that means is that our library functions, when you call them, if the processor is idling, waiting for input, it's going to blink that LED, indicating that the processor is active. So as long as that heartbeat LED on RB15 is blinking, you know that your program is executing code. This library function right here is used to configure the serial port. That serial module is called a UART, and we're going to discuss that in quite a bit of detail later on in the semester. This parameter right here, default baud rate, is used to specify the speed at which characters are going to be sent over that serial link. This library function right here, print reset cause, what that does is when you power up your PIC24, you reset your PIC24 and you call this function, it's going to print out some informational messages that tell you what caused that reset. Did you press the mClear button? Did you power up the PIC24? Was there some sort of interrupt that occurred? So this is simply a utility function that is nice to include as part of your startup of your PIC24. Finally, in order to know that your PIC24 is connected to the serial port, we include this line right here, which calls a function called outstring. This is a function provided in our library. It's going to output a string to the serial port. This macro right here, hello message, is an automatically compiled string that's going to indicate your program name as well as the date when it was compiled. That way you can tell that you've downloaded the correct program into your PIC24, because the string here is going to contain the name of your program. This infinite loop right here performs the function of the echo.c program, which it waits for a character to be typed from the keyboard from the serial port. When that character arrives, it's going to be placed in this temporary variable here called UA_C, which is declared in main. At that point, we're going to increment the character. That means if you type in an A, when we increment this character by 1, it's now going to become a B, and that's what we're going to echo back to the screen. The reason that we're incrementing the character is because we want to know that the PIC24 actually actively read that character and did something with that character before printing it back. If the receive and transmit lines of your serial port were shorted for some reason, then you could actually simply see the same character that you typed without the PIC24 even doing anything. So this gives us a warm and fuzzy feeling that the PIC24 has actually read the character, processed it in some way, and then sent it back out the serial port. So to summarize, this program demonstrates 3 library routines that interact with the serial port. This outstring subroutine that accepts a string or print an entire string to the port. This incar function, what it will do is it will wait for a character to arrive from the serial port, and once that character arrives, it will return it, and you can save that into some temporary variable. This output car function, it will output a single character to the serial port. It's different from this, which outputs an entire string. This outcar function outputs only one character. Here we have programmed the PIC24 with the echo.c program. This information right here, reset cause, device ID, and fast RCOS of PLL, is all being printed out by this print reset cause program. It's going to tell you what caused the reset, which in this case is power on. I turned power on. It's also going to tell you the device ID. In this case, I'm actually using a slightly different PIC24 than what's discussed in your book, and it tells you the revision number of that particular device. Here, this print reset cause is also going to tell you what clock option we're using. Here we're using the fast RC oscillator with the PLL, which is going to be the default option used for most of the programs in this course. Finally, this message right here that's called echo.c, built on this particular date at this time, is being printed out by this outstring hello message. This hello message is the compiler generated string that is actually this particular string right here. this message reset cause power on was printed because I powered on the PIC. What if I pressed the M clear button? How is this going to change? That's going, if I press the master clear button, that's going to cause the PIC to reset and re-execute this program. When it does that, it now prints out a different message called reset cause master clear assertion. We're going to talk in just a minute about how we can actually detect whether or not we had a master clear assertion or we had a power on. At this point, let's go ahead and demonstrate the echo.c program. Here it says this is waiting for me currently to type a character in from the keyboard. So there's two ways I can do that. One, I can simply type a key in the keyboard. I'm going to do that. I'm going to type an A on the keyboard, lowercase a. Notice that the lowercase a was actually echoed as a lowercase b. That's because this lowercase a came in here, was incremented by this program, by this statement here, and then it was that incremented character was outputted. Let me type a different character here. I'm going to type in a capital E. When I type in a capital E, it gets echoed as a capital F, because once I increment that character, it's now going to be incremented to the next character. So a capital E increment is going to be a capital F. And that's what I see incremented here. I could also type a character here. In this case, I'll type a lowercase t and then hit send, and that will also do the same thing as actually typing something in this field. Here, a T was echoed as a U because the next letter in the alphabet from lowercase t is a U.